Good morning, everyone. Welcome to the first tutorial of today. It is held by Haniel Barbosa, who is one of the senior technical leads of Team CVC5, which I'm also a part of, I have to admit, just as a disclaimer. So he will give a tutorial on SMT solving for verification. And as far as I know, it is centered around using CVC5. And having said that, the floor is yours.
Thank you, Aina. Can you guys hear me if I speak at this distance? I don't know if test. I think I have to be closer, right? All right. So thank you for the introduction. I apologize in advance if I'm slower than normal, but like I'm a bit jet lagged. So let's go slowly but surely. So I'm gonna talk about SMT solving in general, giving an overview, also mentioning several kinds of applications you can do with them. And we're going to show examples. A good part of this is going to be centered around CVC5, also with like some exercises that we're going to do together of like how to solve some problems, see some things in action. So I hope you enjoy it, and please just interrupt me if you have a question. They are welcome, and that's it. So I would like thanking the invitation. I'm very happy to be here. It's my first time in Japan. I've always wanted to come here. I'm very happy also to be giving this tutorial at ATVA. Also, part of this work has been funded by like several agents. And for CVC5 in general, there is more information in the website if you are curious about all the support we have had. All right. These slides, like they came together with material from several people who have, like, at some point in time, allowed me to use them. So I'm always very thankful for this. There are several references across the slide deck. I'm gonna send this to the organizers afterwards, so I guess they can be made online for the website. Like if people are curious to check. In the end of the slide deck, there is a very large set of references, and across them, as I talk about some techniques, I'm going to put some references, so that can hopefully be helpful also. All right, so in terms of what we're going to do today, we're going to do an introduction. So this is like a two-part tutorial. So like the way I organized it is that in the first part, I'm going to focus on SMT in general, giving this overview, talking about the kinds of things you can do with SMT solvers, talking in detail about the different theories that are supported by these systems and how they can help many different kinds of problems effectively. And then if you are interested in a given application, as long as you can fit your work in some of these functionalities that the solver provides to you, you're going to be able to leverage them. And then we're going to focus on some applications, and then some of these applications are going to trigger this work in producing and checking proof certificates, which has been a big focus of people working around CVC5 in general and in the SMT community also. So I wanted to talk about that as well. All right, so let's go. So I like to start talks with this slide because it captures a little bit how I think about these things. So there are many different kinds of things that we do with formal methods. And one thing that is very important for formal methods to be effective in practice is that you use automated reasoning tools to discharge things automatically, and it can aid users in many different ways. And then what has been proved to be the case across the decades is that very often, like the kinds of automated reasoning tools that you are using are SMT solvers. So they have become a backbone of the usage of formal methods in many different kinds of settings. And this is what has motivated so much work on these systems and like so many things around them. But how this came to be, right? Like, so automated reasoning in general, it started a while ago. And it started mainly focused on solving problems in first order logic, in doing theorem proving. And this was using a wide range of methods like resolution, superposition, tableau calculi. So across the decades, these were several different kinds of ways in which you would try to solve problems that you had phrased using first order logic that is very general. It gave you a lot of expressivity, but also it was expensive to solve the problems. And this has led to limited success of these approaches. However, in the last decades, things have improved, luckily. And this was thanks in large part to the higher and higher usage of effective procedures for decidable fragments. So the idea was not to apply a general method to solve your problem, but to identify fragments of your problem that were amenable to efficient procedures and then combine them in a way that would allow you to solve the whole problem, but leveraging the particular properties of these fragments and reason modularly about them, and then being able to do things more effectively. So this was thanks also in large part to what was called the SAT revolution in the late 90s, early 2000s. So there had been breakthroughs both in the theory and practice of SAT solving that allowed them to become much, much more efficient and solve problems much more effectively. However, this was not enough if you are thinking like in the many kinds of applications that you can build around automated reasoning, because you are often interested in some things that require more expressivity than what Boolean satisfiability can give you. And this was where SMT came about, because it's combining the support for things that you can phrase in first order logic, but also leveraging SAT solvers in combination with this usage of these domain-specific procedures. And then you had a gain both in expressivity and in scalability. There was a loss of efficiency that you have because you're doing more abstractions, you are handling things that are more expressive, and so on. But this has proven to be like a sweet spot that led to a big advancement in the usage of formal methods applications built around SMT solvers. So this is what the focus of our tutorial today, right? Like to give an overview of SMT, the kinds of things you can do with them, and what are the kinds of applications, some kinds of applications, sorry, that you can build with them. So to give a flavor, an initial flavor, we're going to go back to several examples afterwards of like what is the kind of problem that we're interested in solving here. So an SMT problem, you are interested in determining the satisfiability of a logical formula, which means to determine if that formula can be true and in which way it can be true. And you are reasoning in a combination of background theories, as we call them. What this means is that if you look in a problem like this, there are several parts of this formula that range over different kinds of theories. So we have in sort of purple, arithmetic. We have in green, general functions. And we also have in red things about data types. So here I have like the selector of a data type, I have constructors of data types, and so on. And these are all the different theories that can occur in a problem, and then you are trying to determine if this formula can be made true while respecting the properties of each one of these theories, right? So I have noticed I keep standing back from the microphone. So I'll try not to do that anymore.
Did it help?
No, but I just try to be more consistent. All right. Yeah, so we have this combination of what we call many-sorted first-order logic, which is first-order logic when you have all different kinds of types that you can have with them, and what we call built-in symbols, which are the symbols coming from the theories. So this is, in this example, the things coming from arithmetic, what we call equality and uninterpreted functions, and so on and so forth, okay? So one thing we're going to do here that we're going to talk in detail is about what are these theories, like I'm going to mention how they can be solved. It's not the focus of this tutorial how we actually solve this problem. It's more about using these features. And then, but what are the kinds of problems that we can solve with them? All right. So, yeah, so SMT solver are these highly efficient tools that are this combination of these specialized procedures. And they have been, given their efficiency and increased usage, allowed many new things to be done that couldn't before. So this helped like in increasing the usage of formal methods, which is something that many people have always been worried about in this field to do. And luckily we have succeeded to an extent to do that. Nowadays, it's funny, like I started my PhD 10 years ago, more than that now. And I have seen like during this time an increased usage of these technologies, and this has been something that I have been very happy to see. Like, so it's exciting to be part of this field where like you see things changing and like the impact of the work that you are doing, leading to more and more usage. So this is old, right? Like in terms this stops at 2019, not so good in generating this plot. So I used the one a colleague did a while ago, but we can see here. I mean, this is Google Scholar, so take it with a grain of salt. However, we have this clear trend of a very increased usage in academia, of course, also in industry. Of SMT solvers. This is counting not only citations, but like just the mentioning of these systems. And what justifies this is that there are many, many more applications that use these systems, right? This is not work done in the core of like developing better SMT solvers. Of course, part of it is, but a lot of this explosion has come in more applications being possible because of the development of these systems and their continuous improvement. There are several SMT solvers. There are some of them that are more popular that I could have included also besides this. But these that I included here are very general SMT solvers. Are the sort of SMT solvers that support many, many theories and are used in several contexts. There are others that are more specialized and so on and so forth. And these are systems that have high impact, right? Like you not only have high number of citations, but then at some point, and you see this with Z3, you get to the point that you are so popular that people no longer even bother citing you, right? Because you become part of the zeitgeist. So like this is what every tool should wish to accomplish. And this is something that has been very successful in some SMT solvers. So there are many applications that use SMT. We're not going to talk about all of them, of course. We're going to focus on some of them, like model checking, synthesis, program synthesis specifically. But there are many, many things you can do because SMT solvers give you a lot of flexibility. By giving you the power to reason about first-order logic with these combinations of theories, you basically can solve any kind of problem because you have first-order logic, of course, but you can solve effectively many kinds of problems as long as you can fit them in your theories or, as we're going to talk about, in some careful axiomatizations. And some of these applications have been more successful than others. In particular, I just wanted to highlight this one because it has been something that has used a lot of work that we in the CVC5 team have done, the analysis of access control policies in the cloud at Amazon Web Services. So they have built this tool called Zelkova, which encodes questions about whether an access policy gives as much permission as an access policy that you trust. So for example, you don't want to give access to users to something that you should not. And then you can solve these kinds of like, you can do this sort of analysis by using SMT. And this is a tool that does this. And nowadays it's called billions of times a day at the cloud in Amazon Web Services. So this is one of the big recent like success cases of using SMT solvers that has been powered by the support of certain theories that allow one to reason about these access control policies, particularly strings and regular expressions. Okay. So there are several materials about SMT, like this tutorial is going to mention several papers about things that are done, how you solve problems. But if you want to get like an overview, there are several comprehensive materials. So we have these 2 books that cover a lot of what is done around not only the logic, but the practice of SMT solving. There are dedicated chapters in these handbooks covering SMT. That is SMT Lib, which is a joint effort of the community, not only to standardize and input languages to SMT solvers, which was something that was very important to help the adoption of the systems, but also to curate a standard set of benchmarks that come from many different kinds of domains, and this has helped a lot the development of SMT solving across the decades. There is SMT Comp also, which is a generally yearly competition of SMT solvers. Like it's very large, it accepts all kinds of solvers solving all problems that you have in SMT Lib, and it's a big, big asset for the community because it allows them to evaluate their systems against each other, motivates like it's some healthy competition. And there is a recent work that like me and colleagues like collaborated in doing. It's a tutorial aimed at beginners, so it goes at a very introductory level, talking about logic, talking about encoding problems, and so on. We have an online version that if you're curious, you can check out in the CBC5 website. There is also a paper that was at the Formal Method Symposium this year about it. All right, so now we're going to start talking about SMT solver functionality. What are the kinds of things you can do with them at a very high level, and afterwards we're going to start talking about the theories and then do some examples, okay? All right, so in terms of notation, just so we are on the same page, we are going to use this just briefly, not in too much detail, but like we are going to refer to values. So like these are going to think about like numbers in integer theory, things like this. We have ways of referring to a list of variables that occur in a formula, substitutions. This is a notion here of like a set of variables being contained in another. This is logical entailment, which means that every way in which this formula can be made true also makes this formula true. This means that you have a way to make this formula true, and this way is captured in this interpretation M. So we're going to mention this, but if you have questions afterwards, please don't hesitate in asking, okay? All right, so at a very high level, what you want an SMT solver to do is, given a background theory that you may have interest, like for example, in that example that we saw, we had a theory as a combination of arithmetic, equality and uninterpreted functions, and data types. So you want to determine whether your formula or your set of formulas is satisfiable, whether there is a way of making it true that respects the meaning of the theories. So what an SMT solver can tell you is SAT, right? So it means that the formula can be made true. There is a way to make it true. It can also tell you unsat, which means that the formula is unsatisfiable, which means that there is no possible way among the potentially infinitely many ways in which you could consider giving values to parts of the formula that would make it true. So this is related directly with the notion of entailment, right? Like, so whether you have or not a model that is consistent with the theory that makes your input, your set of input formulas true. And what you would like is that if the formula is satisfiable, you get such a model. If it's unsatisfiable, you get a justification, a proof, for example, why there is no such model. It's also possible to get unknown as an answer. So these are the 3 standard answers as prescribed by SMT-lib that you would get by an SMT solver when trying to determine the satisfiability of a formula. And if you are in a fragment, logical fragment that is not decidable, then you are open to the possibility of getting unknown, because there may be no terminating way to determine whether the formula is satisfiable or not. So the solver may just run out of resources, or it may just have applied an incomplete procedure, because you may, even if you are reasoning on a fragment that is decidable, that you have an algorithm, a terminating procedure to solve the satisfiability of that problem, you may just apply something that is incomplete, but it's generally faster in practice. So you generally have these 3 kinds of answers. So in terms of basic functionality, this is what you get out of an SMT solver. But then there are several different things that you can do with this, as I mentioned. So one of them is to get a satisfying assignment. So if you have a series of variables in your problem, it's to get like the values that these variables would have that make the formula true, according to the theory that you have in question. So you would have a way to represent this assignment. That would be a valuation, a mapping from the variables you have in your problem to values. And the guarantee that you have is that if you were to assign the variables to these values, then your formula is true without needing any more valuations to variables. One thing to note is that in regular SMT solving, your variables are not only constants, but you also may have functions, as we had in that example. We had uninterpreted functions, symbols that you can apply to others, and then you would also get in the satisfying assignment a value to these functions, right? So say a lambda term corresponding to what function is that. We're going to see some examples of this. All right. So another thing that you may be interested, because why generally do you want a satisfying assignment? So an example is when you are trying to encode, we're going to mention this afterwards, there is an example about that. When you're doing software verification, you may have encoded into a formula that you fed into your SMT solver, whether a condition holds for your software, and if that condition does not, then you may want to have a counterexample for why it does not. And in the way that you generally encode these problems, this would correspond to getting a satisfying assignment that would correspond to a counterexample that your software does not do what you wanted it to do. But this counterexample may contain spurious parts. So one thing that is also helpful to get out of SMT solvers is this thing that we call a SAT core, which is a subset of a satisfying assignment that suffices to make the formula true. So you can think of this as a subset of the variables that occur in your problem, and then you are going to get the, the invariant that for all the variables that are outside the subset that you consider, so this would be these y's, then no matter which value they take, you still have that the formula is satisfiable, which means that the values that these variables y take do not matter for the satisfiability of the problem. So this is an interesting property that you can have when you are getting this satisfying assignment, because you are going to get a sort of minimal counterexample, something that's going to give you more information about why the condition that you wanted to test, whether it was satisfied or not, is not. Okay? In the same way that we have cores for satisfying assignment, we may have what we call an unsat core. So this is the idea when you are trying to determine the satisfiability of a set of formulas of an SMT solver. It tells you that that set of formulas is unsat. And what do you do with that? So something that you are interested in knowing sometimes is what are the parts of your formula that are responsible for the unsatisfiability of the problem. So an unsat core is a subset of the input formula that suffices to make the formula unsatisfiable. So necessarily, this core, as we call it, has to be itself unsatisfiable, and then it may even have other properties, like being a minimal unsat core, which means that if you were to remove any part of it, then it would no longer be unsatisfiable. However, this is something that some solvers provide, this functionality, not only of having unsat cores, but trying to minimize them. There is several approaches to try to minimize this effectively. However, this is generally an NP-complete problem in itself, like just to try to minimize, or maybe undecidable, depending on the theory that you are in. So it's often the case that solvers do not guarantee to you that the core that they are generating is minimal, but they try to reduce in reasonable ways. Because if you get a core that is just the input formula, and it could have been smaller, then this is not very useful. Okay? We're going to see some examples also where we extract unsat cores of formulas. All right, so another thing that you can get out of solvers, out of some solvers is not the case. These functionalities that I'm mentioning, it's things that solvers could do in principle. Not all solvers provide these functionalities. Getting satisfying assignments, getting unsat cores is very common, but getting proofs, for example, is not as common. Because to provide some of these informations, you have to do more instrumentation in the solver, and this may not be the focus of that particular solver development. So, but what is a proof? It's an object that justifies why the set of formulas is unsatisfiable. And the idea, we're going to see some examples afterward, is that this justification is checkable. So you have a way to efficiently determine whether that justification can be correct. And it gives you a way to derive the reason why a set of formulas is unsatisfiable. And then there are several kinds of domains where it's very important to have this. We're going to mention some afterwards. But there is a lot that goes into this. Okay? All right. Okay. So there are other things that you can do. So these are these features, as we go on, they become sort of less common in terms of solvers providing these functionalities directly. But there are some solvers that also allow you to extract interpolants out of formulas. So if you have like two formulas that you give to the solver, they are unsatisfiable, but then you want to get the reason, so you have this interpolant that is something that stands in between these two formulas, right? Like it's entailed by the first and itself entails the negation of the second. And you are generally interested in this interpolant being only over the intersection of the variables that occur in these two formulas, and this has several applications in many domains, in formal verification and so on. And some solvers provide this functionality by default, computed in different ways. Some do this based on proofs, some do this based on other ways of generating the system, these objects. All right. So similarly, you have something called abduction. So there are some solvers that can generate to you a solution to an abduction problem, which is sort of similar to interpolation, but is slightly different. So here you have the notion that you have a context, which is this gamma, and then you have a goal, which is this negated phi, that you want to be entailed by, you want phi to be entailed by gamma, so you want phi and not phi. You want gamma and not phi to be unsatisfiable, which is what would correspond to the entailment between gamma and phi. However, it is not the case that this entailment holds. It's not the case that gamma and not phi is unsatisfiable. So you may be interested in answering the question, what could I add to this problem that would make it unsatisfiable? How could I augment my gamma that would make it sufficient to entail phi? And this is the abduction problem that also has many applications, and it's something that some systems can also generate and can be useful in different applications. Right. Finally, the last one I wanted to mention is quantifier elimination. When you have, again, you have a formula that ranges over variables, and you want to generate a new formula where you have eliminated some of these variables. So this is called like a projection, and then this depends. So some theories assume quantifier elimination. You have to be able to have that entailment holding, and then some solvers provide to you the facility to apply quantifier elimination. And all of these features, I'm mentioning them as general things that some solvers support and so on, but CVC5, for example, is a solver that natively supports all of these features for some of its theories. Finally, you can also do optimization, which in particular CVC5 is being extended at the moment to support natively, but other systems like MathSat Z3 have support for this. There are several frameworks in which you can also do it. And the idea is that for when you're doing optimization of SMT solver, you not only want to find a satisfying assignment, but you want to optimize some objective, right? So you have some metric about this satisfying assignment that you want to guarantee that your satisfying assignment preserves. And then some solvers provide this functionality, and you have the same sort of problem, right? That you have to determine modulo a theory that you want to find an assignment, but now you have added another restriction, which is that this must minimize or maximize an objective function, and how do you leverage this in the search, and so on and so forth. So when you are a solver developer and you are interested in solving these sorts of problems, then what you are really worried about is how to better incorporate the characteristics of solving these problems together with the general functionality of just determining if a formula is sat or unsat. All right. So we have all of these different things that you can do with solvers, right? And this is what powers many of these applications that we have mentioned before that use SMT solving. But this is all based on the ability of you to phrase your problem in a language that these systems accept. So what we're going to talk about now is about the background theories that many SMT solvers, well, so some of SMT solvers at least support each of these theories, and like some support all of them. Z3 and CVC5 tend to be the most broad ones in terms of support, but they are not necessarily your choice for solving a problem in these theories, because some other solvers may be better than others at them. A good resource to try to determine this is to look at SMT comp, for example, because it has these yearly evaluations in a sense also of the systems to see how different systems behave in different logics. But in general, what you want to do is to try different systems, because you do have the fact that these systems, they support the same input language, this SMT lib language. We're going to show an example of it, what it is. So there is no harm in trying to see like what are different systems behaving. They often have complementary techniques to try to solve the problems. Okay. All right, so for the examples that we're going to do now, so I'm going to use CVC5, as I mentioned, and in particular, I'm going to use the Python interface of CVC5, which is a very straightforward way to build SMT problems, and also gives you the ability to write Python programs, which are simple enough often to write. You can also, however, directly use the SMT lib interface, as I mentioned. For this, you would need a binary of a system. So here, you can, if you go to the CVC5 website, for example, there is a part of downloads where you can download different binaries for different architectures and so on. In the CVC5 website, also, there is a link to a web server that is running an online version of CVC5. It's something that you could consider also. Or you could install it using pip, for example. So as I have here, right. So there are different versions of CVC5 available at pip. There is just CVC5, there is CVC5 GPL. This is using some functionalities in CVC5 that requires a GPL license, so this is why we have these two versions. But for the examples that we're going to do here, if I remember correctly, just CVC5 should also be enough. And if you are courageous, you can also try this. I have not tried this, so like I take it with a grain of salt, but I guess it should just work. All right. So yeah. So like in the examples, as we're going to do them, we're going to write these small Python programs. And then, again, if there is any question, please interrupt me. The focus is not on showing you in detail like what is the syntax and so on. I'm going to mention it as we go. But the idea is to give you a flavor of how you would use this and how you would use these different theories. Okay? All right, so there are many theories that are supported by SMT solvers, and we are going to, in the end of this part, we're going to mention why these many theories have come to be, what is the motivation for having all of them. And they range over many different kinds of reasoning that you could do. So you have the idea of reasoning about functions, you can reason about arithmetic, you can reason about floating point representation or bit vector representation of numbers, which is useful when you want to model how arithmetic is performed inside machines, of course, in hardware. You have strings, you may want to model data structures, which you would do with arrays, with data types, sets, and so on and so forth. So initially, uninterpreted functions and arithmetic were the most common theories in SMT solvers. They powered a lot of things, and then all of these other theories evolved out of necessity of having dedicated reasoning procedures to solve problems effectively in domains that would benefit from them. Okay? All right, so equality and uninterpreted functions. So the idea of this theory is to have first-order logic, general first-order logic, when you have free functions, when you have equality. And here, one thing that I forgot to mention is that we're going to focus on quantifier-free fragments at first. So the way these theories are defined is generally that you are interested in solving problems without quantifiers, because this is when you are generally in the decidable fragments. So this is going to be the focus that we're going to show. And when you're reasoning on this theory, you want to solve problems when you want to have these following properties that hold over the symbols that you have, right? Over the functions that you have, you're going to have congruence, and over equality, you have the common properties of equality. And then you can have, for example, the necessity of encoding a problem that you would solve with these constraints like this. And then systems that SMT solvers, the way that they solve problems like this is generally using a congruence closure algorithm that is described in these papers that we have here, for example. This is proposed originally by Nelson and Oppen several decades ago. And this was extended to better work in the context of SMT solving, in the architecture the systems implement. There were some tweaks that were necessary, and this was done by Nieuwenhuis and Oliveiras and other people afterwards also. So let's go and see how we would write this problem that we have here, both in SMTlib and also using this Python interface for CVC5, okay? So, test, okay. I think it still works. All right. Okay. So, oh no, what happened? So if you want to use the CVC5 Python interface, assuming you have installed in your Python the support for it, like you could do with pip, for example, you would do this, and this would give you all the ability to use the functionalities provided here. One thing I wanted to mention is that this Pythonic interface of CVC5, it is meant to be compatible with Z3's Pythonic interface, which was something that was developed many years ago and has led to a bigger adoption of SMT solving also. So it was a good starting point to have an interface that would allow people to use not only Python programs for Z3, but also for CVC5, for example. So if you want to solve the problem that we had here, so here I have this function f, I have this function g, and I have these constants a and b, right? So I need to encode all of these things. I need to declare these functions, these symbols, and then what they range over to be able to reason about the satisfiability of such a problem. So the way I would do this is that I would declare an uninterpreted sort, which is the set of values that the constants can take, a and b, right? So I could do it like this, for example. I would declare two functions, f and g. So f is a unary function whose name is f. So this is the Python variable standing for the symbol that is functional that I declare with this construct here, okay? And then this is a unary function that returns a value of the same type. I also have the binary function g. So it takes two arguments of this type and produces an argument of this other, of the same type, okay? I have the constants a and b, which I can declare directly with this notation. So I have these two constants that are named a and b, and they are of sort u. Okay. All right, so these are the symbols that I can use to build my problem in this theory, the theory of equality and uninterpreted functions. So I am going to build a set of constraints which correspond to these equalities that I have here. And then what I'm interested is in, are there values for, first, for this sort u that is any sort, is any type, any set of values, that I can assign to it such that a and b are of this sort, and then f is a unary function of this sort, g is a binary function of this sort, such that these equalities all hold, okay? This is the sort of problem that we're interested in solving when we want to reason on this theory. All right, so what you can do here with this interface is that you can declare a solver, and then you can optionally annotate it to work directly for a given logical fragment. And this is an information that can be useful, in particular for CVC5, to know in which logical fragment you are, because then it can target better the algorithms it's going to use to solve that problem. So when you are interested in solving a problem that contains equality and uninterpreted functions only, you are in a UF logic. And if you have no quantifiers, you are in a quantifier-free fragment. So this is something that is very useful to know this jargon, to know this terminology of the logics, because then you can give more information to the solver when you want to solve a problem. And then we are going to declare the constraints that correspond to these equalities here, okay? So we have this FFFA that is supposed to be equal to B, right? This is the first equality. So here I am telling to the solver, consider this, that has to be true, when you are going to determine whether this problem is satisfiable or not. I can add then the other two constraints. The first one says that g of f of a, b is equal to a, and then finally the last one says that f of a is equal to a, okay? And then I can determine the satisfiability of the problem. And the way that we can do this is by calling this function check. All right, so given that I have this, I can run this program, and it didn't work, of course, because I had a typo. Now it should work, and it did. Okay, good. So this problem is satisfiable, okay? So the solver has successfully determined that there is a way to assign values for the different elements in this problem, the uninterpreted sort, the functions, and the constants, that makes the constraints that I have here satisfiable, that make them true, okay? But what is this assignment? So I have the ability to also query for a model. And then if I do this, it's going to give me such a satisfying assignment. And this is a way of viewing these assignments, okay? So we have a few elements here. Let's go over them slowly. So this thing here corresponds to a value of the sort u, okay? So both A and B were assigned to the same value of this sort u. This is what these first two elements of the assignment here are saying. F was assigned to a function, since this is a function, so a lambda term that given an argument, it's a unary function, it always produces this result, which is that same element of u. And G was assigned a binary function that also produces that same element u. So this is a very not enlightening assignment, however, that is sufficient to make this formula true, okay? So the point is that you can then, if this were modeling, if your F and your G's and A's and B's meant something to you when you encoded your problem, you had here a way to visualize how the system gave them values such that the formula was true, okay? Can you think of any way that we could make this formula unsatisfiable? Some constraint that we could add here that would make it unsatisfiable? Yes?
A g of a, b equals b, because then this should collide with the last constraint.
Like this?
Yes, because I mean, we know that f of a is a, and then we know that g a b should be a, and then we say it's b, so it should be false. At least that's my interpretation.
Let's check. No, it's still SAT. I mean, you were getting into something here, right? Like that since f of a is a, we know that f of a, and therefore you're going to get that a is equal to b because of as you were describing it.
So we would need to add that they're different, a and b.
Exactly. Yeah. So I mean, you would not be able to get something as unsat here if you just had equalities. At some point, you must have these equalities. But I think the idea that we're going at is that what you would get if we did this, and then if we did this, we would get that it's unsatisfiable because of the collapsing that we have of f of a and a here. So yeah, so this that we just did here is the ability that we had like a set of assertions, and then we had a check of satisfiability, we queried for a model, then we had a new set of assertions added, which is something that you can do in what is called an incremental mode of SMT solvers, and then you can check the satisfiability. So as I mentioned, like if you had this situation where the system gives you an unsatisfiable result, it may possibly give you more information about that in the same way that you can get a model when the problem is satisfiable. We can try to get an unsat core when it is unsatisfiable. What is the subset of the assertions that make this formula unsatisfiable? If we try to do this, it's going to fail. Because first, I had to write like this. And then second, because I did not give an option. So the thing here is that when you initialize a solver, it has a default mode. And by default, it's not tracking the necessary information that would allow you to produce an unsat core. The motivation for this, and it's very common among SMT solvers, is that it's more expensive to solve a problem while you're doing this bookkeeping. So the way that we could set this option is like this. So if I did this, then now the system would be able to give me an unsat core. And then note that, so it gives this unsat core as a list of the assertions of these formulas that we added to the solver. And note that this one does not show up, right? Because to determine the unsatisfiability of this problem, then that is not necessary, okay? So CVC5 can also give you a proof of this. So if I had this option, I mean, it would not only allow me to get an unsat core, but I could give you a proof. And then it would generate this object here, okay, which I'm not going to mention in detail now. I'm going to mention afterwards, but this is a justification as a series of inferences of why CVC5 was able to determine that this formula is unsatisfiable. So this is just to give you a flavor that there is a lot that goes on here, right? There are several things that the solver is doing automatically, very efficiently, to be able to reason about a problem such this and show that it is unsatisfiable, okay? All right. So now we're going to talk about more theories, but any further question about what we did so far? By the way, so just because I wanted to. So I want to show you just how I would write this problem if I were using SMT-lib. Then this is a Lisp-like notation that you use to declare your symbols and then your formulas. So I'm writing the same thing that I had written here in Python, right? But this is how I would write it in SMT-lib. Then these are the commands to declare constants, to declare functions, to declare a sort, okay? Then I can write the equalities. So the syntax is prefixed, so I have to write like this. Then I have g of f of a equals a. And then I have f of a equals a. And then I also have the other one. And then with this, I can run any SMT solver that accepts SMT-lib, which is almost all of them. And then here I have just the CVC5 binary that if I run in this problem, it's, of course, I wrote it wrong. What did I do wrong? Yes. I wrote G partially applied. So there is something funny here. So G is a binary function, right, that I declared here. And I had written it wrong by applying it only to an argument. I wrote just G of A. And the error message that CVC5 wrote is that I cannot partially apply a function unless you prefix your logic with this. This is because CVC5 has support for high-order logic. So it can reason about partial functions and equalities between functions, things like this. It's a limited capability that it has for reasoning on that fragment, but it can do that. But we are not going to talk much about that. So now, then it would be able to determine the unsatisfiability of the problem. So everything that we write in Python, you could write in SMT-lib, because in the end of the day, like or in an extension of SMT-lib, I should say, because CVC5 supports more things that are in SMT-lib. All right. Okay. So coming back here, so here we're talking about EUF, and now there are many other theories, as I mentioned. So another important theory is the theory of arrays. It's really a theory of maps. So like it's the idea to represent symbols that behave as arrays that you can model like this. And the properties that you are interested for constraints in this theory are these properties here that restrict how you reason about selecting elements of an array. So this is, as you would expect, to access the value of the array in a given index, and also to generate, to store a value in an array. So you have this store function, you have this function here that represents the selection of an element, and then you have the behavior that you would expect that if you store an element in a position in an array, and then you access that position, you're going to get that element, and so on and so forth. So this is to say that these are the logical properties that restrict how you can reason about the symbols of this theory. So if you want to solve a problem, and then you want to use these functionalities, you want to use this theory, then you have to be aware that this is how these symbols, the interpretation of them, is restricted. So it's also common to have the theory of arrays of extensionality, and this is that like when arrays are different, it's because there is a position in them that has different values. So the way that solvers generally solve this problem is you have equalities here, so you have a combination of reasoning about functions and equalities, but also you have to reason about these axioms here, okay? And then there are efficient procedures implemented in solvers that are using data structures and efficient algorithms to determine when to apply these inferences, and so on and so forth. And then we have this sort of constraint that you could try to solve in the same way that we did in the previous example. You would write your problem using a theory that corresponds to having the properties of arrays, to have the symbols available, and then to ask for the satisfiability. Okay? So we can do the same thing that we did before. But rather than having these things here, I'm now going to have two different sorts, one for the indexes of an array and one for the elements of an array. Then I'm going to have an array. So there is this array sort. It's a method to build a sort out of sorts for indices and elements that gives you an array. So you would pass this, so it's a parameterized sort. And we also had I and j, right? So I have an array A, I have I and j, which are indices to access elements of this array, and then I have stores and access functions applied to this array. So I could write like this. So I have these two constants here, right, that are of the sort that I use for the indices of the array. Now I am going to create the constraint. The logic that operates over arrays in SMT-lib is this one, AX, when you just have only arrays. Say that I don't want proofs at the moment, but then how I would write what I had there. So I had a store, right? So it's a store of the element at j of a in the position I of a. So I would write it like this. So this is the first store that I have. And in that, so the store gives me an array. So you take an array, and then you put something there, and you have as a result a new array. And then in the position j, I'm going to put the value of a at position I. Okay, so this is the first array that I'm generating here. And my constraint is that the array that I have here must be equal to the array that I would have by putting in position j the element in position I of A, and the resulting array, I put the element in position j of A. So this would be store of A, j, A, I, A, j. Okay? And then I can test for satisfiability. So you think this is satisfiable or not? Should be, right? It is, good. Unless the solver is wrong, but if I don't trust the solver, I can get an assignment. And then it's going to give me this assignment. So in this assignment, it's telling me, so this is a way to say that I have a constant array, which is a function that maps every element of this set I to this value here. And so I have this value from the set E, which is a set of elements, that is this guy. And then both I and j are the same index, which is this at I0 of set I. Okay? So there is a way to make this formula true, which is have an array, and then that has at every position the same element, and have indices that are the same. This is a way to make this true. How could I make this false? No, sorry, not false, unsatisfiable. I mean, there is a simple way, which is we could try to break this assignment, right? So the first thing we could try to do, for example, is to make I different from j. Would that be enough? It wouldn't, right? It wouldn't, because if I do this, then I just can have an array. So now I is different from j, but I have an array that has at the respective positions for I and j yes, so at position, what's happening here? Ah, yes. So the way that you represent a value of an array is via a series of stores, right? So you have a constant array, which says that at every position you would have this value, and then over that you do a store, in which at the position I1 you put this element. And this gives me exactly what I would need to have the satisfiability of those constraints. So if given that that's not enough, what is that I could add here that would be enough to break this? Yes. Sorry?
I is different from the element in AJ.
Yes.
Yeah.
If I do this, then it's well. Oh, it's because I wanted to write this. Then I wrote wrong in the other one. Yeah. But this is what gets there. Yes, exactly. Because what I require here with these three things together is that AI has to be equal to AJ. And that cannot be the case if I have this here. So yes, so this is what you would, sorry, you have?
May I ask you a question?
Yeah.
So this, so the fourth line that you have here, it's a theorem, isn't it? I mean, this first formula that we wrote, yes, now, line number 12.
This one?
Yeah.
When you say a theorem, you mean that it should always be true?
Yeah.
Well, okay. By itself, yes.
By itself, yeah.
Yes. Because what I did here, is I cheated, right? Like, so to make this formula unsatisfiable, I had two new things that were themselves inconsistent. And I could see this if I were to get an unsat core, and then that part would not be in it, right? Exactly. So there is actually no way to make this formula unsatisfiable that depends on this, because as you said, like, this is always true.
Thanks. Yeah. But you can also prove it. You can also prove that that is theorem using your subsolver, right?
Yes. So if I wanted to prove this, then I would assert its negation, and then I would expect it to be unsatisfiable. So if I do this, then I have the guarantee that indeed this is always true because its negation is unsatisfiable. So yeah, so you can use SMT solving. That's a very good point, thank you. You can use SMT solving also to do theorem proving, which is if you want to show that something can be true, you assert it and you check for satisfiability. But if you want to show that something is valid, you assert its negation, and then you expect that to be unsatisfiable. Right. So there are many other theories, right? So like as I mentioned, and then arithmetic is a theory that was, together with equality and interpreted functions and arrays, the big focus of SMT solving, because it allows you to model a very, very wide range of problems, and then you can, as long as you fit into one of the theories, use the efficient procedures, but moreover, arithmetic is very vast, and there has been a huge amount of work done across decades in many different ways of solving arithmetic problems. So there is, in a sense, a set of theories that is arithmetic itself. So when you are solving satisfiability problems ranging over arithmetic, you are actually combining procedures that range over many different fragments. So if you fit in some particular fragment, then you could apply some dedicated procedure. And there has been lots of work, like in having dedicated procedures if you fit into particular fragments. But most notably, the biggest distinction that is done among SMT solvers is linear arithmetic and nonlinear arithmetic. Because you can, I mean, this can give you efficient procedures, but in this, the difference is very stark, because as soon as you go from linear to nonlinear, you may go into undecidable fragments when you have integers, but also, even though nonlinear arithmetic with reals is decidable, but it is doubly exponential. So it can be very expensive to solve problems there. So the logics in SMT-lib, these logics as I was writing, QF, AX, etc., they allow you to distinguish between these different fragments for some of them. For difference constraints, there is a particular logic for this. It's called IDL or RDL. For linear arithmetic, you would have LIA or LRA. And for nonlinear, you would have NRA or NIA, which represent these different fragments that you have. And therefore, they can tell the solver what are the different procedures that it could restrict itself to when trying to determine the satisfiability of these problems, okay? And there is still very active research, like improving arithmetic procedures in SMT, given their importance. This is informed also by research that happens in related fields, like the computer algebra field. There has been more collaboration in that regard in the last years also. Yeah, and then to do an example, we could try to solve this problem here. Are there real solutions for this equation? But in the interest of time, I am going to directly right here. So this here, I have these x and y and z real variables, okay? I created a solver saying that I am in the quantifier-free, nonlinear, real arithmetic fragment. I can say I don't need proofs. And then I added here this constraint to the solver. And then I can ask the solver whether this is satisfiable. And here, this is a way to just write some simple Python that, like, if it's sat, I'm going to directly print the model. Otherwise, I'm going to print unsat. Okay? And then, if I run this, CVC5 is going to solve this problem, and it's going to give me a model. So in this assignment, I have that the formula is true. Okay? So one thing that I wanted to point out is that what makes a big difference to solve this problem is how I tell the solver where the problem lies, in which fragment. If I were to say that it is in this fragment, so this is a different logical fragment, at least in what could potentially be in the formula. So this includes not only real, but also integer, arithmetic. I would say it also includes uninterpreted functions and arrays. So this is how I would tell the solver that I could have a problem involving all these different elements. And now I have the same problem, okay? The same constraint that I had before. I have not changed the meaning of the variables. They're still real variables, and the operations that I have here also have still the same semantics. But if I were to try to solve this problem, CVC5 would not solve it in any reasonable time. It would just hang. And the reason, what I wanted to illustrate here, is that by knowing beforehand that I was in this logical fragment, I as CVC5, I would know that I can maybe just apply this more expensive procedure that I have, that is a decision procedure for nonlinear quantifier-free arithmetic, and this is what is used and then solves this problem. Okay? In this case, CVC5 is solving this using cylindrical algebraic decomposition, which is a very expensive doubly exponential procedure that it is not using when you are in this more broad logic, because you would be sort of in an unbalanced way dedicating more resources to reason about arithmetic, whereas you have other elements in your problem. So it can make a difference, like how you set the logic. So one thing also that as a user of SMT solver should be aware is that solvers tend to be highly configurable because you are solving a broad range of problems. There are many different implemented procedures. Some things are on by default, some are not. And in doubt, like, you could ask developers, you could look into the documentation, you could try to restrict as much as possible the logical fragment that you are in, and so on and so forth. Okay? Right. And as before, like, we could ask whether there are solutions where the variables are only positive, and then in this case there aren't. I have to do this. Yes, so there are no only positive solutions to this problem, and then you can also get a proof. That again involves a lot of stuff. Okay? All right. So other theories of interest, including reasoning about machine arithmetic. So this is very important if you're doing hardware verification, for example, or if you're reasoning about software, but you want to be precise about how the values are represented as machine integers, machine floating points, and so on and so forth. So when you have, however, problems involving these logics, like you have to reason about how they are actually represented. So like the nice algebraic properties of integers and reals, etc., don't hold directly. You have to reason about overflow. You have to reason about these values when they're treated as vectors. So you are doing shifts, you are extracting values, and so on and so forth. And the way that you handle these theories in SMT solvers, what has been more successful across the decades has been to rely on procedures based on bit blasting, which is to reduce these constraints over these problems after some very smart things that you can do with simplifications, abstractions, and so forth. But then you reduce this to a SAT problem, to a problem involving only Boolean reasoning that is exactly satisfiable to the original one. And then you can use off-the-shelf SAT solvers. And then, I mean, it's still a very active area of research, how to improve solving methods for these logics, given the high interest that exists in reasoning about these theories. So one thing that we could do here is, for example, to consider something that's going to show up when you talk about software verification a lot, which is program equivalence, basically. But program equivalence here in a very simple manner, in which the program that I have is just to compute like the absolute value of an integer, of a machine integer. And then I have all these different ways that I claim are ways of doing the same computation. So the first one is the standard one that you could think of, that if the number is negative, you just negate it. Otherwise, you have the same number. But you could do some smart bit manipulations to do this operation more efficiently, right? And then what you could do here is to try to prove the validity of the equality between this way of doing it and this way of doing it. As the Shiro had proposed, you can just negate the equality and then check if that is unsatisfiable. So if we wanted to do that, so I have written here this as this Python program, right? And then I have this constant x. So this is the way to declare this bit vector sort that is parameterized by the bit width. So I can tell how many bits I can have in the bit vectors. So in the Pythonic API, I can use directly the symbols to represent, for example, the shift that I do to the right. This is the reference implementation, where I have that if then else, right? If this condition is true, I yield this result, otherwise I yield this one. And then here I have the other alternatives. So what I'm doing here is to create a solver that's going to reason about quantifier-free bit vectors, and then it is going to assert that these two implementations, ABS-ref or ABS1, ABS-ref or ABS2, etc., that they are different, and then I want to have that these are unsatisfiable, right? Because if they were satisfiable, it meant that there was a way to give values to x that made the result of this computation versus this computation to be different. So this is what you are often interested in when you're testing program equivalence, for example. One thing to note is that what I'm doing here with this command is to remove previous assertions from the solver. So this is a way to reset just part of the solver, just the assertions, so that I can invoke it again. Because if I had like that after this first constraint here, the problem is unsatisfiable, to add more constraints to it, it's going to continue to be unsatisfiable. So it would not test what I wanted to test, right? Right, so if I run this, I would get 3 unsat answers, which means that in each one of these implementations here, I have an equivalent computation happening. Okay? All right. So in sort of a similar manner, so like we also have the floating point arithmetic theory that is also meant to model how machine arithmetic is happening with floats. This is a much more complicated theory because floats can be very complicated. This is following the IEEE set 754 standard, and then you have a wide range of operations and so on and so forth. And also similar to bit vectors, the way that the state-of-the-art operates is generally reducing to bit blasting. So to quickly do an example before we have a break, I wanted to show like the most common property that people like to emphasize when they say how floats are like bad behaved is that associativity does not hold, right? So if I want to write this as an SMT problem, so I wanted to test that this equality here is not valid. So what I could do is to write this program here, and I am declaring 3 floating points variables of this float 32 type, where I'm giving 32 bits to represent the values. I have a rounding mode that is required whenever I'm doing operations with floating points. You have to specify how you would round if you were to need to, because there are different rounding modes. And then I am adding the constraint that these two ways of adding. So I'm first adding A to the result of BC above, and here I am adding C to the result of adding A and B. And then I'm saying that these have to be distinct, and is this satisfiable? So if there are values for A, B, and C such that this is the case, then this is going to be satisfiable. Which, as we know, is the case, right? Like, because addition is not associative in floating points. And then here we have like these beautifully represented values of floating points with this rounding mode that yield like different results for addition. So one thing that I also did here was to use a model given by the solver to evaluate an expression. So this is also something that you can do. So I have this eval function that is provided by the model that, given an arbitrary term containing the variables for which I have values in the model, I can evaluate this operation. So in this case here, I'm evaluating exactly what would be the additions of A to BC and of C to AB, right? And then as we see, we get different results starting at this precision here. Okay? All right, so we are going to stop here because we have a break. And then after the break, we're going to continue talking a little bit more about theories and then talk more about applications. Thank you. See you soon.